Hello everyone, my name is Du Xiang. The title of our paper is Program Verification Enhanced Precise Analysis of Interrupt-Driven Programs Vulnerabilities. I will introduce our work from the following four aspects: background, preliminaries, approach, and experiments. First, let's start with background. Interrupt-driven programs are widely used in aerospace, medical equipment, and other embedded systems. Data race and atomic violation are two of the most common types of vulnerabilities in IDPs, short for interrupt-driven programs. Due to the non-deterministic happening of interrupt service routine, the behavior of an IDP is usually unpredictable, even for the same input. Therefore, traditional testing and simulation techniques are hard to detect data race and atomicity violation vulnerabilities of IDPs. Existing static analysis techniques usually ignore the accurate guard conditions of each statement, which leads to a large number of false alarms, while program verification usually faces the state path explosion problem. Now I will introduce some preliminaries in our work. In IDPs, a data race occurs when two tasks with different priority ranks access the same memory address simultaneously, and at least one of them is a byte. For example, when the main task is reading a global variable v, an ISR arrives and it will write v. Then a data race occurs between the two events of v. In concurrent programs, programmers often assume some code block to be atomic. It means the execution of the code block cannot be interrupted by another thread. Otherwise, the program may exhibit some unpredictable behaviors. In practice, we often require that the data manipulation of the code block is equivalent to that of a serial execution of them. If this property is violated in some case, then we say an atomicity violation vulnerability occurs. For example, suppose that one atomicity code block contains two consecutive reads of a global variable v, then we wish the two read operations should obtain the same value. However, if another thread happens between the two read operations, and it may modify the value of v, then the two read operations will get different values. Then we say an atomicity violation vulnerability occurs. Not all atomicity violation vulnerability lead to program errors. We focus on these four types of harmful atomicity violation vulnerability. Next, we come to the approach. The architecture of our approach is shown in the picture. Our approach can be divided into two phases: potential vulnerability analysis and potential vulnerability validation. We first use a program preprocess to deal with the C language characteristics and convert the original program into an SSA intermediate representation. The program information extraction process is used to extract those information required for vulnerability analysis, including all shared variable operations, the accurate control flow graph of each task, and so on. Then, two vulnerability analysis algorithms for potential data risk and potential atomicity violation vulnerability analysis are employed to analyze all potential vulnerabilities according to the definitions, respectively. In the potential vulnerability validation phase, we try to employ program verification to automatically identify those true ones from the generated potential vulnerabilities. For each potential vulnerability, we try to find an execution path of the program which triggers it. If such a path is found, then the vulnerability is true. To achieve this, on the one hand, we need to accurately consider the guard condition of each statement. On the other hand, we need to consider all possible interleavings of those ISRs. The overview of our idea is the static analysis method is used to detect all data risks and atomicity violations. The vulnerability validation eliminates most false alarms. Though the validation phase may filter a few real vulnerabilities, the method is still effective. The two algorithms illustrate our potential vulnerabilities analysis algorithm. With the accurate global variable operation information of each task, it can quickly scan even large-scale programs. Furthermore, we have proved that all data risk vulnerabilities can be reported with these algorithms. To validate if a vulnerability is true, we need to find an execution path which triggers the vulnerability. If such a path is found, then we can conclude that it is true. Otherwise, it is prone to be a false alarm. Given a potential vulnerability, to employ program verification to find an execution path that triggers it, we first properly insert the high priority task into the low priority one, and obtain a sequentialized program, which can then be handled by existing program verifiers. Consider the data risk vulnerability in the figure. The auxiliary vulnerability, OPNAM, is initialized to 0 in line 7. Given that E2 executes before E1, we use comma expression to let OPNAM increase by 1 when E2 is executed. When it executes E1, if E2 has already been executed, then OPNAM should be 1. Hence, we add an assert statement before E1. If a counter example of this property is found, when it executes E1, then it is a path that triggers the vulnerability. For an atomicity violation vulnerability, we can generate the reachability property with the similar method as shown. Finally, I will introduce experimental results briefly. We have implemented our approach on top of CPMC. Our implementation supports nearly all C characteristics. To show the effectiveness, and the scalability of our method. We evaluated it on both an academic benchmark and 24 real-world IDPs. The benchmark consists of 31 programs. It contains 120 data races and 49 atomicity violations in total. For atomicity violations, as we can see in the table, we found all vulnerabilities. The number of shared access events range from 6 to 40,000, and an increase in the scale of events will not lead to a significant increase in time consumption. The vast majority of cases are detected within a second, even for 40,000 shared access events. The analysis time is still quite acceptable. We have confirmed that all those validated ones are true vulnerabilities. We can also observe from the results that our method finished the analysis of all the 31 programs in only 34 and 18 seconds for data race and atomicity violation analysis, respectively. To evaluate our method in industry, we have collected 24 real-world IDPs. All of these IDPs are open source and available online. From the results, our method can analyze these IDPs with thousands or even tens of thousands lines of code in dozens of seconds. Different from the academic benchmark, for real-world programs, the number of real vulnerabilities is unknown. However, as we have proved in theorems, our potential vulnerability analysis phase could report all possible vulnerabilities. That's all. Thanks for watching.